why IC engine simulations are required. And I'm going to be talking from a simple level. Let's start with an easier level first. So to answer that question, tight emission control is required. Okay, and achieving these emissions. So when we are talking about emission control, we are talking about reducing the emissions. And to go about reducing the emissions, a thorough knowledge of the combustion process and the fluid flow process and the mixing process is required. Just trying to guess what happens inside an engine is not going to lead us anywhere. Experiments are good and they are very, very expensive. We'll talk about experimental techniques in the upcoming slides, but that's the general idea. So to get the conversation started, let me ask a couple of simple questions. Can anyone give me some examples of emissions? What are some of the emissions that we need to reduce in an IC engine? CO2, NOx, lead. Lot of good answers. Okay. All right. That's great. Mayur gave a new answer, particulate matter. That's a good one. So the primary emissions that people care about are NOx and soot, which is soot is also referred to as particulate matter. Can anyone tell me what is NOx? What does that X stand for? Exactly. 1, 2, or potentially higher. So NO and NO2 are the primary pollutants that we care about, which are quite dangerous, and we couple them together and we refer to them as NOx. All right. So how do we go about reducing these emissions? What are some of the existing strategies that are present in current automobiles to reduce NOx and say to reduce soot? What are some of the available options? Catalytic converter, SCR, that's nice. Carburetors, no, not really. Muffler, nope. Fuel injection, yes. So the modern day fuel injectors, they possess some characteristics which can reduce emissions. And like bunch of other combustion properties, like Pradeep is saying, spark timing can be adjusted, exhaust gas recirculation, we can use an oxidation catalyst, multi-point fuel injector, a lot of good answers, yes. All right, so the whole idea is, there is, depending on the type of combustion that's taking place, if it's a diesel engine or if it's a gasoline engine, then what's going to happen is your combustion strategies are different, and the way the combustion takes place and where the fuel is converted to products, it's going to change. And because of this change in a mechanism, you need to think of emission control in a different way. Again, this statement might be a bit too complex to understand at this point. Hopefully by the end of this presentation, it'll be clear. Okay, so how should you as an engineer think about optimizing an engine? Before I go through this, can you guys tell me, like, how many of you are currently pursuing their MTech? If you're pursuing your MTech, just type in your names, or just type in that you do, so that I get a feel for how many of you are doing your MTech or MS, basically PG, some kind of postgraduate degree. Okay, Deepu is pursuing his MTech. How about others? Okay, so it seems like we have a couple of them pursuing their MTech. How many of you are either doing your BE or BTech? Rakshit, all right. Cool. So the major portion, okay, there are a couple of ME students as well, but basically it's all BE BTech, and okay, completed BTech, that's fine. All right, cool. So since majority of you are still in your BE BTech, I'm going to be kind of optimizing the content of this presentation towards BE students. So the ME students in the call might find certain explanations a bit simple. All right. So how should you as an engineer think about optimizing an engine? As a mechanical engineer, I'm pretty sure engine is something that everyone is interested about. And the primary goals that students have is, to make the combustion process more efficient, to reduce the emissions. So let me start with a simple question. So what does it mean to make the combustion process more efficient? Nearly 100% combustion, Vipul, that's a good answer. Complete combustion of fuel, that's good. More power output, that's good. High work output, that's good. Less pollutants, that's correct as well. So now all of these answers are correct, but they are partially correct. And as you will see later, when you're talking about combustion, right, you're having some amount of fuel. Obviously, you want to burn all of it. What happens if you do not burn all the fuel? What's going to happen? You're going to get CO, that's correct. And this actually leads us to a new form of emissions called as UHC. Does anyone know what UHC stands for? UHC. Unburnt hydrocarbon, exactly. So if you do not have, for example, if you do not have the right burning rate, you are going to get a lot of unburnt hydrocarbons. So with respect to optimizing combustion, yes, you want to burn all the fuel, but you also want to burn it at a correct rate. And this is what is called as heat release rate, also called as HRR, and sometimes referred to as apparent heat release rate. Okay. Now, you need to understand the combustion process first. Okay. Again, apparent heat release is just a scratch on the surface. There are so many topics that you need to learn first. And only when you learn that, you will be able to understand what the problem is. And only when you understand what the problem is, you will be able to propose a solution and possibly test it. Now, to test your solutions, you can use CFD at your current level. You do not have access to experimental data or the equipment. So how does combustion process take place? So in your understanding, can you describe to me how the combustion process takes place? Like, what are the things that affect your combustion process? Yes, as Vipul Mani says, fuel and air, basically fuel and oxygen, but in reality it's fuel and air. The temperature, the ignition temperature, pressure and temperature, basically, you can club all of them into one thing, which is the thermodynamic properties. Vaporization, that's correct. Good. Basically, if you're using spark or compression ignition, tuning those parameters, that's correct. Atomization, very good. Wall thickness, that's a good answer. I'm really happy that someone said that. The flow of fuel, okay, now we are slowly starting to circle the same answers. Valve timing is also correct. Right, so slowly, we are now, we basically have exhausted all of our options. So let's try to understand how combustion takes place. And I'm going to first show you the simple view. So you have your fueling system and you have your air intake system, right? They both interact and you get a fuel and air mixture and they basically combust and you get emissions. All right. So if I have to think about optimizing the performance of your engine, I can make the mixing process more efficient. So can anyone tell me what are some of the current strategies that exist in automobiles to make the mixing process more efficient? Multi-port fuel injection, good. A turbocharger, I like that answer better. Piston design, yes. Swirl, tumble, supercharger, carburetor. We have multiple superchargers, and basically we are quoting the things that popular bikes, popular two-wheelers advertise these days, right? Or popular cars like dual spark, like DTSI, that's dual spark, GDI. Most of your answers seem to be towards fuel injection and spark ignition. All right. But all of them contribute towards a better mixing at the end of the day. And then combustion process. We need to make the combustion more efficient. So what does this mean? One of the answers that we've already talked about is, we need to make sure that all the fuel burns correctly. And then we also need to make sure that the fuel burns at the right rate. What else is there? How else can we make the combustion more efficient? So Ujjwal says flame front. So like what do we do with the flame front? There's a stoichiometric ratio of 14.1. Okay, so good octane number, pressure ratio of the fuel, more O2. Again, guys, think about what you are achieving when you're saying optimal air fuel ratio. How does that actually affect your combustion efficiency? Can anyone tell me? Because I saw that 2 or 3 people said optimal air fuel ratio. Why does optimal air fuel ratio help increase combustion efficiency? And some people are saying rich fuel and lean fuel, no localized combustion, right? So you need to understand how actually combustion takes place, right? So how combustion takes place and how combustion leads to emissions, all right? So it seems like there is some confusion. For example, Avinash is saying that more turbulence is required. So what does more turbulence do? Like, how does it help? Avinash, do you think you can answer that question? It can mix better, but what is the level of turbulence that's required? What if you are using a carburetor engine where the fuel and air is completely mixed and you don't have atomization because things have already been atomized and everything is perfectly mixed? Okay, so think about those questions, because that actually helps you understand where you have holes in your knowledge, where you have gaps in your knowledge. You need to fill these gaps first. Like when you say more turbulence, try to understand why a higher level of turbulence helps achieve higher efficiency. You need to think about those questions at an undergraduate level or your MTech level. So once you understand that, you are able to think of strategies, and then you are able to design solutions. So let me ask you one more question here. How are emissions created? Now, if you're an MTech student, you might have studied about this in a textbook. If you have already studied about this, don't answer this question. They are byproducts, okay? All right, byproducts of what? How do we understand emissions? Like, why do we get NOx? Why do we get soot? Exactly, Ujjwal is exactly correct. It's basically simple chemical reactions. You can think of your fuel and air as reactants, and depending upon the thermodynamic conditions, basically the pressure and temperature in your combustion chamber, you are going to get products. All right, it's just a simple chemical reaction. If you understand the chemical reaction very well, you can understand how different species or different reactants and products are formed. And based on that, you can come up with catalytic converters. So one of the things is catalytic converters are efficient only at a particular stoichiometric ratio, right? And that is all because at a particular stoichiometric ratio, the reactions takes place in a particular way. You get certain amount of species, certain number of species, and those species can be trapped by your catalytic converter, right? So the people who design catalytic converter or the oxidation catalyst or DPF, they have thorough knowledge of the combustion process and how different emissions are formed. Without understanding that, you will not be able to design systems. Okay, so this is a simplified view. So now let me actually try to explain to you how complex this system is. We are going to start with the simplified picture that we have in mind, and we are going to build upon it. Even the picture that I'm going to present right now is not complete. There's a lot of missing pieces here as well. So the first thing you need to start with is your fuel components, right? Your fuel contains aromatics, alkanes, alkenes, and different types of hydrocarbons. Depending upon these hydrocarbons, the vaporization characteristics is going to change. Can anyone tell me how I can quantify vaporization characteristics? What is the thing that I need to measure in order to see how the fuel vaporizes? Octane number. No, octane number is not right. Octane number basically tells us the knocking tendencies. Flame point, yeah, that's correct. Latent heat, yes, that's correct. But these are not the only right answers. Ignition temperature, flash point, flash and fire point, these are all related to when it starts to ignite. But what about vaporization in general? How can I describe the complete vaporization characteristics of a fuel? Atomization is wrong. vapor pressure, partially correct, diffusion, partially correct. So, this is your first gap in knowledge, right? So let me just, try to explain this. You might have all heard of a fractional distillation column, right? A fractional distillation apparatus is used to basically take your heavy hydrocarbons, and you can use that to simplify or basically break down that hydrocarbons into different hydrocarbons. Now, the heaviest hydrocarbons get settled down in the lowest height, and as the vaporization takes place, or if the vaporization takes place a bit slowly, or sorry, not the vaporization, like as the phase change takes place slowly, the hydrocarbons get settled down at different height. Now, similarly, your single fuel, for example, if you go to the gas station or a fuel station, fuel pump, and get gasoline or diesel, it contains several thousand species. It's not just a single hydrocarbon. It's not hectane, it's not heptane, it's not octane. It's a mix of several hydrocarbons. Each and every hydrocarbon has its own vaporization characteristics, and hence, to describe a fuel's vaporization characteristics completely, we need to come up with something called as a distillation curve, which basically says how the components in the fuel vaporize at different rates. And that's just one thing. And people dedicate their entire masters and PhD to basically understand the fuels. All right. Next thing is physical properties. So what are some of the physical properties that are important for a fuel? I'm talking about physical properties. Mass, well, odor, yes, but we are talking in terms of combustion, right? And so odor is not a big deal. Viscosity, melting point, I don't know why you said melting for a liquid fuel, but that's not the right answer. Flame front temperature, Neeraj, is not a physical property. Flash and fire point, I wouldn't call it as a physical property, though I can see why you call that. Viscosity is a good answer, or even density. There is thermal conductivity. There is vapor pressure, right? So why is viscosity important? What happens if the fuel does not have the right viscosity? What's going to get affected? Flow is going to affect it. Mainly atomization process is going to get affected. Okay. So, and how the atomization process is going to affect it, I'll talk about that shortly. The next thing is your injection system. You need to inject the fuel at a particular injection pressure. Now, depending upon the type of engine it is, your injector can have a single nozzle or it can have a multiple nozzle. So some people said MPFI, right? Multi-point fuel injector. Multi-point fuel injector basically contains multiple nozzles in a single injector. And how should the injector be placed in the engine? Should it be pointing down or should be tilted at 45 degrees? When should the injection take place? What is the start of injection? How should the injection profile look like? Right? There are so many things you need to understand. So maybe I will ask another question. Can anyone tell me what's the common injection pressure in a typical diesel engine? In a passenger car diesel engine, or a truck diesel engine, what's the common injection pressure? Okay. So a lot of people who are saying 20 bar or 200 bar are completely wrong. The answer is around 3000 bar or 4000 bar. I mean, like a few people in the top pointed out correctly. Daryl and Raj Mehta, you guys are right. So the injection pressures are really high. Okay. How about your gasoline engine? So for example, let's think of a port fuel injected engine or a direct injected tumble engine. What's the injection pressure going to be? 1800 bar is ridiculously high. 4000 bar is ridiculously high. So for gasoline engines, especially for port fuel injected engines, the injection pressure is really low. The only person who got an answer close is Ujjwal. It's really low. It's around 5 bar, and nowadays it's going up to 10 bar, right? So the injection pressure is really low. Why would one particular fuel have a higher injection pressure and the other fuel have a different injection pressure. You need to understand all of these things. Why do diesel engines don't have port fuel injected engine? Why do gasoline, like, you need to think about those questions, right? And to answer that question, you need to have a thorough knowledge of how your atomization process takes place, and also understand how the mixing process takes place and what's the combustion characteristics, how it's different between a gasoline engine and a diesel engine. So this is where you have to think a little bit more further and understand the atomization process. So how does the atomization process takes place? And when the atomization process takes place, you have liquid droplets. The liquid droplets can actually hit on the wall and it can form film, and then the film vaporizes, and then two droplets can collide with each other and it can coalesce. It's called coalescence. All right, you need to understand all of these things, because when you understand all of these things, right, you can actually look for solutions to optimize your engine in all of these blocks, right? You can try to increase your combustion efficiency by trying to optimize the injection pressure. So one of the reasons why diesel have high injection pressure is that it has been found that higher injection pressure in diesel engines helps with NOx and soot reduction. Okay, and these have been done through extensive experimental and computational study. It's not something that you can just guess. Okay. Similarly, this is just on the fuel side. So now let's take a look at the intake side. So now, if you have a diesel engine, then your intake system can also have some amount of exhaust gases introduced into the intake system. This process is what people refer to as exhaust gas recirculation. So can anyone tell me why exhaust gas recirculation is used for? What is the use of EGR? People who are saying supercharger and turbocharging, it's completely wrong. No, that's not right. EGR is not for that. As Raj Mehta is pointed out, using the exhaust gas recirculation helps us reduce the combustion temperature. When you are reducing the peak combustion temperature, you are able to control the NOx. Okay, again, if you're a BE student, there is a good chance that you might not know this, but this is the type of stuff that you need to learn. You can't just simply be learning about catalytic converter, what it does. You have to understand how EGR works and why it's required. All right. Okay, so this is just your intake system, and depending upon your load condition, when I say engine load condition, depending upon if you're going downhill or if you're going uphill, if you have more passengers, then your engine load condition is going to change. And if it is a gasoline engine, the engine load is controlled by a throttle. So when you're pressing the accelerator, or when you're if you're in a bike, when you're just turning the accelerator, then there's a throttle valve which controls the amount of air that goes into the engine. Now, depending upon the amount of air that goes, you have a O2 sensor in your engine that basically senses the amount of oxygen. And depending on that, it basically releases the right amount of fuel to achieve close to stoichiometric condition. And this control is all done by your electronic control unit. Now, understanding this system is also required. All right, so it doesn't stop there. Now you are at a point where you're starting to think about your air intake. It can contain exhaust gas recirculation if it's a diesel engine. And this air needs to enter into your combustion chamber. How is it going to do that? It's going to get through the intake manifold or intake port if it's a single cylinder engine. Now, for your intake port, you need to think about what the swirl number is, what the tumble value is. Can anyone tell me what's the difference between swirl and tumble? Okay, looks like maybe people are still typing the answer. That's okay. If you don't know it, that's fine. So I'll explain to you what swirl and tumble is. So and we'll do that towards the end of the call, where I actually show a demonstration of an actual engine simulation where you can see the details. So now if you've designed your intake system, then you need to think about how the air is going to enter into your combustion chamber and how it's going to get compressed. And this is where you worry about your valve dynamics. So when should your valve open? What should be your valve lift? And when should your valve close? All right, and what's the profile for it? You need to understand all of these things because the valve dynamics determines your trapped mass and also your engine blow-by. So trapped mass is basically the mass inside your combustion chamber at the end of the intake stroke. So once the intake valve closes, you are basically going through the compression stroke of your engine. If you're talking about a 4-stroke engine, and in the compression process, you need to start with the amount of mass and fuel, or if it is like a PFI engine. This amount of mass basically tells you the amount of work that your engine can produce. So it's very important to achieve the right amount of trapped mass. If you have less mass, then your engine is going to have really less, like low amount of work. If your trapped mass is too high, your pressure is going to be really high. And basically you're creating a bomb. Your engine can explode if your trapped mass is super high. That is why there is a limit on how much turbocharging you can use. If you pump in a lot of air if you compress a lot of air inside a combustion chamber, it's going to blow because the mean effective pressure is going to be very high. It's going to cause structural damage. So you need to understand these things as well because they determine your efficiency, basically your thermal efficiency. So with these two things, you can get your fuel and air mixture. And your fuel and air mixture is what is called as a charge condition. So Raj Mehta asks an interesting question. What is engine blow-by? So what happens is when we study cycles, when we study like a 4-stroke cycle, right? We basically think of it as a very simple model. There's intake stroke that's taking place, compression is taking place, and then combustion and exhaust. But oftentimes when the compression stroke takes place and once combustion takes, like when the piston is moving towards the top dead center, your intake valve is still closing. So a little bit of air is lost through the intake, and it also is lost through the crevice volume. So what is the crevice volume? So you have between your piston and your liner, there's a small gap, right? So air can actually escape through that gap. That is called as engine blow-by. Similarly, when your exhaust valve opens, some amount of the combustion products can actually escape through the exhaust, still unburned fuel. So this is called as engine blow-by. So blow-by can also cause emissions. And for example, you might have heard of the term called as crankcase emissions. So crankcase emissions is caused by engine blow-by. All right. So now, after discussing all of these things, we are still at the fuel and air mixture, which people call as the charge. So charge refers to your fuel and air mixture. And depending on the charge condition, you can have it as premixed, partially premixed, and non-premixed. So if you're thinking about a carburetor engine where the fuel is injected upstream, like the fuel is injected in a carburetor, the fuel has enough time to mix with the air. So the fuel and air are well mixed. That's called as a premixed charge. Now, if you have a port fuel injected engine, then what happens is your fuel and air will mix, but they are not completely mixed. You still have some amount of liquid fuel in your domain. That would be an example for a partially premixed charge. And if you take your diesel engine or if you take your direct injected gasoline engines, then they are non-premixed because the fuel and air, they mix just a few milliseconds before combustion takes place. Now, depending on how the charge condition is, your combustion process, the way the chemical reactions take place is completely different. So based upon the fuel and air mixture, the other thing you need to worry about is your wall heat transfer. So wall heat transfer accounts for a lot of energy loss, because when you're losing heat from combustion, you're basically losing efficiency. That's an efficiency point. And for that, you need to understand how engine block is designed. You need to understand what type of cooling solution is required, because if you don't cool the engine, then what's going to happen is your engine is just going to undergo thermal damage. Okay. So you need to cool the engine, and you need to cool it the right amount. You cannot take excess heat from the engine. If your cooling system is too efficient, if it's removing all the heat, then the engine is not going to do any work. Now, in addition to that, there is also engine packaging. If you open your bonnet in your car, The engine is not the central unit, right? There's a lot of powertrain components. You have your differential, you have your, depending on the car that you're driving or depending on the vehicle that you're driving, you have your flywheel and your gearbox. All of this have to integrate and they all have efficiency points. There's a loss of efficiency in each and every stage. So understanding that is another way to improve the efficiency of a complete automobile. Now, all of these things, right? Like at the end, it completely depends on your fuel chemical kinetics, right? In real combustion, what actually happens is your fuel and air do not get converted to carbon dioxide and water vapor. There are several types of reactions called as primary reactions, secondary reactions, and tertiary reactions that take place, that take your fuel components and they break it down into several hydrocarbons that you might have not even heard about. So before getting converted to carbon dioxide and water vapor, there are thousands or if not 10,000 reactions that take place. And the study of these reactions is called as chemical kinetics. People have devoted their entire lifetime to study, for example, how hydrogen burns, how methane burns. And they have come up with chemical kinetics mechanisms. And these mechanisms are very much required to understand how the emissions are formed. So this picture is still not complete. There is so many pieces here. I've not included that because I have to keep in time the level of the audience and also the time. We don't have a lot of time. All right. So I hope, as engineers, as undergraduate engineers who are really passionate about IC engines, you need to focus your time on learning these advanced topics. Only then you will be able to, like when you're joining a company, even if your aim is to just get through an interview, understanding things at this level is going to help you crack a job very easily, right? So when you read about engines, try to understand about these topics. And when you go and sit in an interview, the interviewer would be surprised that you know this much, because this is exactly the thing that people in the automotive companies talk about these days. So when you're basically engaging them with conversation at the same level, they are going to be extremely impressed with you. And I know that in a lot of universities, these topics are not covered. At an undergraduate level, you learn only simple things. They don't tell you that there are so many things. So, the lack of exposure is also a reason. Yeah, I agree with you, Rakshit. You're right. So, okay, as engineers, you also need to understand, okay, see, in order to understand the problem, right, you need to be able to look inside an engine. So we'll now discuss some of the experimental techniques that are available, starting with something called as a shadow graph. It's also called as Skill-Lync imaging. So let me just play this video. So on the left, you have non-vaporizing fuel, and then on the right-hand side, you have vaporizing fuel. Let me play the video one more time. So this black jet represents your fuel. So that's why it's called as a shadow graph. You're seeing the shadow of the fuel spray. Now, the way Skill-Lync imaging works is it looks at the density difference. So anything that is really dense is going to appear dark, and anything that has a very low value of density is going to appear white or light in color. So here on the left-hand side, it's non-vaporizing. That's why things remain dark for a while, because you have liquid left in your domain. On the other hand, on the right-hand side, you initially have liquid, but then since it's vaporizing, its density is dropping. And that's why you slowly don't see the vapor anymore, because it has completely vaporized. And think about this. Look at the time scale. This is all happening in microseconds. So for those of you who do not know what microsecond is, it's 10 power minus 6 seconds. So this is really, really small. So you're looking at 0.05 seconds, right? So this entire process takes place in a very short amount of time. And, experimental techniques exist to actually capture data at such a resolution. And people who develop these type of techniques, they have very good knowledge in engineering, optics, and they're able to understand what the problem is, right? And that's why they're able to come up with these type of solutions. If you look at experimental data, most of the equipments that are being made, they are not made by Indian companies, right? They're all made by companies outside of India. So let me show you something that's more amazing. So ultra fast synchrotron X-ray helps you provide something called as a full field phase contrast imaging. So here you are looking at an injector, And this is the nozzle of an injector. So you have one nozzle here and the other nozzle here. And this right here is called as an injector needle. That's correct. So inside an injector, you have a needle that actually lifts up and down. It's basically like a gate valve. When it actually opens, flow comes in. When it closes, the flow stops. And the needle is controlled by your electronic control unit. Okay, it opens at a particular rate and it closes at a particular rate. Okay, so here we are actually using X-ray to basically understand the flow behavior. Now look at this injector, right? In the injector, you have two nozzles, and the flow from one nozzle is quite different from the other nozzle. Now people are looking at this level of detail to understand the flow and combustion process, right? So as engineers, you need to be on track. It's very hard for you to get access to these type of equipments, but there are papers available, there are textbooks that talk about these type of techniques. You need to be reading those type of textbooks. So if you're reading local author textbooks just to pass your exams, you are getting nowhere. Okay, so but the nozzle geometries look alike. Exactly, the nozzle geometry looks alike. So that's the whole idea of turbulence, right? See, even a small change in the geometry, for example, if there are like electron microscope images of injectors, you will see that the injector actually has a lot of the surface is not smooth, and one surface is not going to look like the other surface. So there's going to be small perturbations, and since the flow is turbulent, it's extremely sensitive to the surface definition of these nozzles, and that is why the flow structure on one side is completely different from the other. Can you suggest some standard textbooks? Yes, I'll be doing that at the end of the call. All right, so now let's take a look at chemiluminescence. So as I said, people devoted their entire life to studying about chemical kinetics. One of the great breakthroughs was identifying the OH radical. So when your fuel actually burns, as an intermediary reaction, there is a radical. Basically, there is a species called as OH, known as the hydroxyl radical, that gets produced. This is understood to be something that starts the combustion process. So here you look at the spark plug. I don't know if you're looking at a mobile device, this image might not be super clear, but you have a spark plug here. You have a spark that starts small and then slowly it propagates, right? Like this is the order in which you look at things from left to right. And you can see that this is how the flame propagates, and capturing this is done through a technique called chemiluminescence, which can take the image. They do some image processing to capture OH, the hydroxyl radical, and that is how these images are being generated. Now, if you're looking at my video, there's an image behind me. You can see that it's a very similar looking engine. So that's actually a spark ignited engine. And you can see that the flame there is also looking very similar to that, to this particular picture. So let me ask one question. Why is the flame not spreading out spherically? Like you can see that this is not a regular shape, right? It has a particular shape to it. What are some of the factors that determine the shape? Air. That's a very abstract answer. Spray pattern. Well, this is a spark ignited engine. So it's a pre-mixed engine. So there's no spray. There's no spray in this case, guys, and it's a pre-mixed engine. It's a pre-mix, which means air and fuel are completely mixed. And there is no liquid fuel. The fuel has been vaporized already. Turbulence, exactly. Now, see, think about this. What's happening is, first of all, this right here, the boundary of this blue flame, right, of this chemiluminescence, this is what people call as flame front. So first of all, when you're saying flame front, understand what flame front means. This is what flame front is. And when the flame is actually propagating, it gets deformed by the turbulence in your domain. So you can think of, I have a very simple example for this. So think of a plastic bag. The bag that you get your groceries, right? So if you go to the local grocery shop, they give you a bag, plastic bag. Now, if you have the plastic bag and if you let it fly, it's going to start flying, and it's going to have some amount of air, and the surface of the bag is going to continuously change its shape. The reason why it's doing is it's interacting with the turbulence in the air, and it's deforming the shape of the bag. Your flame front is very similar to that. It's not a plastic bag, obviously, but it can interact with the turbulence in your air, and the flame can get wrinkled. W-R-I-N-K-L-E-D, wrinkled. Okay. So again, this is a slightly more advanced physics. You need to know a little bit of combustion to appreciate this. But that is why people are interested in knowing about combustion and how it interacts with turbulence. So do we assume that fuel air mixture to be steady state for these 70 milliseconds? In this particular case, that's how the experiments have been done. Well, when you say steady state, it's not like the velocity is zero. There's still some amount of turbulence there. You cannot visualize turbulence. You can, there are some techniques, but when you see the image, for example, when air is blowing, right? You know that air is blowing because of the noise it makes, and if you see a tree, the tree is going to move around. But imagine you are seeing wind inside a room, and you are just looking at from a window, and there is no trees. How will you know that the wind is moving? How will you know that air is moving, right? You have to throw some kind of a particle or a paper to see how it actually moves. So yeah, in this case, turbulence exists. You are not able to see it. And that is why the shape of the flame is getting changed. If you don't have turbulent flow, then the flame is going to be called as a laminar flame, and it's going to spread out at a laminar flame speed. Laminar flames are extremely symmetrical. So if I have a single point and if the injection takes place, if the condition is laminar, the flame is going to propagate equally in all directions. Now that is why in gravity, in zero gravity, when people burn things, for example, there's a lot of videos on YouTube where you can actually see a flame being simulated outside Earth, like in zero gravity. So what happens is the flame actually spreads equally in all directions. It's called as a spherical flame front. Okay, all right, so moving on. In addition to that, there are other devices. You have temperature and pressure sensors. Okay, you might have heard of these things, so I'm not going to talk about that. So what are some of the merits and demerits of experimentation? So one of the advantages is that experimental data can be very accurate if you do it correctly. But oftentimes experimental data is prone to errors because the person who is actually setting up the experiment makes some mistakes. Okay, and the mistake is very costly because each and every experiment, for example, the chemiluminescence image that I just showed you guys, for a single data point, for a single spark timing, for a single air and fuel mixture, this experiment is going to cost around $20,000. Think about that, right? So $20,000 is like 13 lakhs. So if you make a mistake, someone is not going to be happy with you. All right, so it's prone to errors. It's very costly. The setup is very complex. You need to know exactly what you're doing to make sure that the data is accurate. Damn, yeah, I understand. Right. So this is why people look into IC engine simulations. It's very cost effective. You can get high temporal resolution. It's possible to collect large amounts of data. Now, in order to be able to use IC engines as engineers, you need to be very skilled. For example, some of you have some application knowledge, basic combustion, basic engines, but without knowing computational combustion and computational fluid dynamics, there is no way for you to understand how combustion takes place. Then you won't be able to do these type of things, right? So if you are someone who wants to get into IC engine simulations, if you want to do this type of work, then you need to start upgrading your skills. There are a lot of job openings in India where, and unfortunately, they are not able to find talented people. And that is why most jobs are still being kept. Like, for example, here in the US, there's a lot of opportunities, right? So people who do their masters, who actually learn these topics, they get jobs very easily. Okay. So now what I'm going to do is I'm going to give you a live demo of how the combustion process looks like. So, and how the data looks like from a combustion simulation. So first of all, this is a software called Convert CFD. So this is a computational fluid dynamics package. So what I did is I'm setting up a port fuel injected engine. This is not a CAD package, okay? So I created this geometry in SolidWorks and I'm setting up the fluid CFD simulation here. So for example, I have my physical models. So for example, I can use this to set up the spray modeling. Again, think about it, right? So when you're setting up the spray modeling, there are so many things you need to worry about. The evaporation, the penetration, mass diffusivity, collision, wall interaction, and so on. I did not include the presentation because, like I said, I just wanted to keep the level to something that most of you would be able to follow. Similarly, with respect to combustion, there are so many things that you need to take care of. There are different types of combustion models that are available, and Converge supports all of these things. So Converge is a popular tool. It's used in pretty much all the automotive companies, General Motors, Ford, Toyota. You know, like when I worked with these companies, you know, they use Converge to run their IC engine simulations and design newer engines, newer piston bowls, intake port optimization, exhaust optimization, EGR optimization, multi-cylinder optimization. You know, all of those things can be done using Converge CFD. So I've already run a simple simulation and I'm just going to show you some data. Okay, so just a second, guys. Okay, so here, for example, this is the pressure trace inside an engine. Okay, on the x-axis I have crank angle, and then y-axis I'm showing the pressure. So your intake stroke completes, compression takes place, combustion takes place. Here the combustion is not taking place correctly. Let's take a look at the mean temperature. You can see that the peak combustion average temperature is around 1800 Kelvin. How is all the basic data or boundary conditions obtained? The boundary conditions are obtained through experimental data. Okay, and you know, for example, if you want to take a look at how the heat is getting released, so we have something called as heat release rate. So you can see that initially the heat release rate is 0 because, you know, you are just doing your intake and compression process. And when the spark starts, your heat is getting released. It has a particular shape to it. And then at some point, the combustion stops. Now you can take a look at integrated heat release, which basically says how much heat is getting released totally. Here we are just releasing 40 joules. That is very, very low. And that is why the combustion is incomplete in this particular case. Okay, so you need to start looking at data at this level of detail in order for you to understand engines completely. So for example, how does the mass inside an engine change? You know, this is how it looks like. You know, like, why does it look like this? You need to understand that. Similarly, your volume trace, your piston, basically, you might have all studied kinematics, right? You might have all studied about slider and crank mechanisms. If you solve those equations, this is how your volume is going to change inside your engines. You need to understand these type of things. You know, you need to understand and deal with these type of data. Similarly, you might have studied Otto cycle or diesel cycle. You would have a value for gamma, which is set to 1.3, 1.4, but in real life, the value for gamma actually changes. Depending upon the temperature, depending on the number of species that you have, the value for gamma changes. So when you're thinking of gamma as constant, that is a very simplified theoretical model. In real engine or engine simulations, it's not like that. You need to be more accurate, right? The simple models helped us long time back, right? And the simple model has been used to its fullest. Like, there is no more information that we can get from the simple model that will help us design new engines. So you need to stop studying that and you need to learn about advanced concepts like what is being shown here. So this is all simple average data. Now let us take a look at more significant data, and this is the post-processing. So I've already run simulation using Converge CFD, and I'm not run it for this particular engine. Let me see if I have a different engine here. So here what I have is a different, it's called as a flow bench, but this is the type of engine that I'm going to be looking at. This is actually a diesel engine port. Okay, I'm looking at a diesel engine port and I'm going to simulate the flow through it. We are going to be I set up this as an engine simulation, and I ran the simulations for it. And let's take a look at some of the results using ParaView. So ParaView is a post-processing tool. It's used by a lot of companies to do advanced post-processing. All right, so first what I'm going to do is I'm just going to open up my engine simulation. Okay, so you can see that the data has been loaded. So I'm going to go to my multi-block inspector and maybe remove the cell data. So the first thing that I'm going to do is, you know, I can investigate the geometry. You know, you can see that this is a helical port. You can see that it spins in a particular direction, right? This is all done by designers on purpose to achieve a particular swirl number. So I'll explain what swirl is. So let me hide the engine liner. So can anyone looking at this picture tell me what is the axis of piston? What is the direction in which the piston moves? Is it the x-axis, y-axis, or the z-axis? Exactly, z-axis, right? So when the flow actually comes through the intake port, if it spins about the z-axis, that is called as the swirl. Okay, now if the flow spins about x-axis and y-axis, that is called as tumble. So when the flow spins about x-axis, that is called as tumble dash x. And when the flow spins about y-axis, that's called tumble dash y. That's it. You know, when we visualize the data, it's very easy to understand. Tumble and swirl are basically measuring angular velocities. Okay, they're measuring angular velocities. And once we get the angular velocities, we divide the angular velocity by the engine RPM to get a non-dimensional number. So that is what your swirl and your tumble are. Okay, all right. So in this particular case, so first, let me do a couple of things. I'm going to first create a clip plane in the domain. Maybe somewhere there. Okay, so I'm just going to cut the domain first. Let us see. I hope it appears okay. There we go. We have a very nice picture there, and I'm enabling a couple of options here, hiding the plane. Okay, so this is a very good picture. So you can see that the valve is already open. So Deepak is asking what is tumble. So tumble is angular velocity about the y-axis and the x-axis. Deepak, does it make sense? When the flow spins about the y-axis, that is called as tumble, or x-axis, it's called as tumble as well. So I have a cut plane in my engine, and let me take a look at the computational mesh. So here I'm taking a look at the computational mesh. You can see that the mesh is bigger in some points and finer in some points. This is all done on purpose. So there's a particular reason. There's a particular reason why the mesh is chosen given a particular size. So what I can do now is I can just color this guy by, say, the velocity magnitude. All right. So here what I'm looking at is I'm looking at the velocity, right? Look at that. This is amazing information. I cannot get this from, I can get this from experiments, but it's going to be extremely costly. Here I can see that the peak velocity is somewhere when the valve opens, because that is where the area is minimal. Just because of continuity equation, the velocity is going to be really high there. And what I can do is, right, using post-processing, I can just, look at the velocity profile. So, let me create a simple line plot. And then what I'm going to do is I'm going to say that this is my first point and this is my second point. And I'm going to be, looking at, say, the velocity. Again, don't worry, I'm doing a lot of things here. You won't be able to understand this, like how I'm doing this right now. But here, what I'm showing is I'm on the x-axis, I'm basically plotting things along the length of the line, and you're looking at the velocity. This type of information helps you understand your engine in a better way. What's the peak velocity that's coming in? You're able to understand where things are recirculating, because when there are recirculation zones, sometimes it's bad for you, sometimes it's good for you. You need to understand all those things. Okay, so all right, so let me first delete this guy. And what I'm going to do is I'm just going to move to a different data point. I think there is one more data point that I have in this particular case. So here you can see that now the piston has moved towards the top dead center. This is closer to the combustion. So you can see that the valves are closed and now the velocity is really low. It's less than 10 meters per second, right? So let me show temperature. And we are going to use a different color map for temperature so that we can see it. Okay, so here you can see the flame front and you can see that the grid is, the computational mesh is different. So here I'm using a technique called adaptive mesh refinement to automatically refine the mesh. So if I go back the previous image or previous time, you can see that the mesh is refined only near the intake valve, right? And everywhere else the mesh is uniform. But when I'm approaching the top dead center, you can see that the mesh is now finer in more points, right? So we are actually resolving the flame front automatically. Okay, and here you can see that I'm measuring the combustion temperature, and let's create another line probe. And what I'm going to do is I'm just going to measure how the temperature varies across the diameter. Let's look at this, and maybe plot the temperature, right? You can see how the temperature changes. You know, the peak is around 2525. I can get a large amounts of data like this. Why is there a bulge in the bottom face? So that's your re-entrant piston bulge. So I can show this. Let me maybe close this graph that I just created, or rather what I can do is I can just a second, guys. I'm going to delete the plot. Okay, and we are just going to hide everything and just show the engine piston. And I'm just going to make the piston transparent, so that you can see through it. Okay, so do you see what's going on now? Keshav, we are creating a clip plane right there, and that's why you see the bulge. So if I move the clip plane, which I should be able to move, you know, maybe if I move it somewhere here and then just click apply, now you can see that the shape of my bowl, the shape of the cut plane has changed. And you can see that the grid is slightly more different here. And the flame front is even more different. So depending on what you get, or depending on where you look, you look at different things. And running IC engine simulations helps you understand everything. Like, you know, there are so many things. I can look at the turbulent kinetic energy, how the turbulence exists in my domain. I'm coloring it by TKE. There's also something called as turbulent kinetic dissipation, and there's something called as turbulent viscosity. These things you need, I don't think at this point you guys understand, but you need to know all of these things to appreciate an IC engine simulation completely. You can easily follow a tutorial in Star CCM or ANSYS Fluent and do a simulation, but you would just be clicking buttons. You will not understand what's going beyond it. So let me go back to my previous time step. And I wanted to show you something more interesting. You know, this is actually a swirl port. The port is designed in such a way that it actually aids in swirl. So what I'm going to do is I'm going to create something called as a stream tracer, or called as a particle trace. And I'm just going to create some source here. And don't worry if you don't understand what I'm doing. They're going to be looking at the streamlines, basically the flow structures. This process can take like 10 to 15 seconds. So just bear with me. How many time steps can be obtained? Well, you can get as many time steps as you want. So in this particular case, I'm just showing you 2 data points. Reality, we are looking at all the 720 crank angles. So here, you know, like I've got the flow structure, and let me actually hide the slice, and you can see how this looks, right? I mean, this just looks incredible. And if I make it slightly opaque, you will be able to see the flow structure. You'll be able to appreciate what's going on. And what I can do is I can then color this guy by velocity, and I can appreciate the flow structures. So how the flow comes in and how it actually swirls. You can see how it actually turns here, and you can see how things are spinning around and how this is a swirl engine, right? Exactly, this is amazing. Yeah, so people, you know, as students, you should be able to study these type of things, and this is the type of projects that you should be doing at this point. Is there an animation of the same animation is possible? Currently, I have not done it because I wanted to do a live demo. If I do an animation, it's going to take several hours. And let me show you one other thing that you guys might appreciate. Let me hide the piston, and then I'm just going to show you the intake port and maybe the intake valves. And let's just make it very like transparent. Right, so here what I'm doing is I'm showing you the intake port. You can see how the flow comes in, how it interacts with the valves. For example, if the valve opens, it automatically pushes the flow in one direction, and then things start spinning around. This is all done in purpose. Now, when you do this, you are creating a lot of TKE, turbulent kinetic energy, inside your, what do you call? inside your combustion chamber, and that is what actually helps you with the combustion process. No, this is just the intake stroke.